Okay, so yeah, today we have first discussion day, and Said will be the discussion lead. But before that, I need to give some. I need to discuss some things. Uh, okay. Uh, yeah, you have sent me the slides. That's fine. And everyone, like the day when you are going to be the discussion lead, make sure that you send me the slides before the lecture. Second thing is like last time I forgot to record the attendance. So I'm giving you two attendance sheets. So one for today and one for the last lecture. Okay. So if you're present, so sign it. And yeah, the first person can also put the date, one for today and one for the last, which was 0121. Okay. Feedback and comments on the, what was this, class participation form 1. Actually, did I make some announcement? I guess yes, related to class participation form 1, right? So first thing, like when you are submitting your class participation form, write down the question, answer, comment, suggestion, anything which you actually stated in the class, right? It is like, let's say if you are suggesting some improvement, then you should have discussed that improvement in the class. Okay. Otherwise, I will not count it. So for the first class participation form, I am okay with that. But for the remaining upcoming ones, I'm not going to accept those kind of questions or comments or suggestion, whatever. Second, when it is about suggestion for improvement or like identifying the weakness or the strength of a paper, it should be more on the side of like a technical contribution of the paper. It should not be like, okay, the introduction is very unclear, or yes, that can be something like which definitely contributes to improve the quality of the paper. But in this class, we will be more concerned with technical things, okay? Also, when you are summarizing, try to highlight the main points or the main insights of the paper, okay? What else? Yeah, I think these are the things which I had in my mind. Okay, I have uploaded the annotated version of paper 1. I mean, I read it and whatever annotations are. So just to give you an idea, like your annotation should also be look like very intensive like that. Okay. I know, I mean, it will be difficult to like for you to like take the notes, raise the questions, make the suggestions, but try to improve your quality. Okay. Uh, okay. Next discussion lead. No one has signed up yet. Okay. Everyone in this class has signed up for the discussion lead. Everyone. Okay. Okay, then I can ask those who haven't and ask one of them to volunteer for the next paper. Okay. Okay. Two absolute points for first two discussion leads. Doesn't matter whether graduate or undergrad. I made this announcement last week to encourage you to sign up for that. And I think it is justified given that uh, the papers were released late. One, second, the people who are going to be discussion lead later in the semester, they will have more experience. They by that time, they already have seen other people how to serve as a discussion lead, and I will give the feedback. So, I mean, they are on advantage. They have advantage as compared to those who are like serving as discussion lead in the first 2 weeks. So in my viewpoint, it is justified and fair, but if any one of you thinks that it is not, then send me an email and tell me why it is not, so that maybe I can change my mind. Okay? Okay, send your slides. Okay, if you are discussion lead, so this is an example where, like, for example, Said is on disadvantage, but people who are going to present later, they will have disadvantage. So you can send, I didn't say this, I didn't suggest this, but what you can do is that you can send me your slides one night before, actually not Wednesday night. Send me your slides by Wednesday night so that I can give you some feedback on how to improve your quality of your slides. And then you can present them in the next day, okay? But it is optional and not required. Okay, and send me your slides, final slides, once you are done with serving as a discussion lead. Okay, for audience, as I said in the last class, have you prepared your question list? Again, this is not required, but please, when you are reading the paper, definitely there are some questions which you have in your mind. So take note and bring up that sheet with you. So maybe we cannot answer all of those questions, but at least it will enrich our discussion, right? Maybe there are some questions which never came to my mind, but you have those questions, okay? Okay, so that's it from my side. And now it will be the, okay, yeah, where is here? And let me start recording. Okay, Said. Sorry? Oh, okay, sorry.
Hello everyone, I'm Saidako, and I'm going to do a quick presentation on the survey we read on microarchitectural side and covert channels attacks and defenses. Here we go. This is really long and I'm not going to read all the text, but these are the two main motivations I found on the paper. And these are just direct quotations from the conclusion of the paper. And essentially, the people motivation is very intuitive. The survey is to give context to new people or give a whole holistic view of the domain field. In this case, it's covert and side channels, and just giving context on different background information as we did in the previous lecture, and covered attacks and defenses in existing work. And the technical motivation, this one I found more interesting because it was a little bit snuck in, which is with the emergence of cloud computing and virtual machining and having a lot of technology in a different location outside from your own, wherever your physical location is, gives a rise to different covert and side channels that are created because of these virtual machines. Now to cover some background information, some of this is kind of review, such as what is a side channel, a covert channel. And then I put the same diagram we had in the same lecture, and it's the one from the survey, where you have, there's three main types of channels, but the survey focuses on timing-based and access-based channels. And then the types of attacks that can be done based on these channels, which is external timing and internal timing. But the survey's kind of meat is section 3, and that's this characteristics leading to these channels. And it covers 4 main ones: instruction execution timing, functional unit contention, state-dependent output, and memory subsystem. Instruction execution timing is kind of what it sounds like. This is different instructions on a machine take different amount of times. A simple example given by the survey is that an addition instruction is a lot faster than a multiplication instruction. And so an attack on this channel would be seeing the difference of these times, and you can determine which instruction is ran based on how long the instruction took, because you know one is faster than other. And this kind of leads into the terminology the survey uses of slow paths and fast paths, if that wasn't kind of clear before. Functional unit contention. Functional unit wasn't clear at first until we reached memory subsystem, but it's essentially the different components of the processor, microarchitectural processor system that make up the processor and have different things working together is the best way I can kind of explain it. So the contention between these, we covered examples like in the cache, where you can have 2 different processes accessing the cache at different times where one it has some of its data in the cache, and then it gets removed in the scheduling, and another process accesses it, and so it creates a miss and attack. And so this is contention, wanting to use the same unit, but the data it accesses isn't correlated to the process itself. Then you have state-dependent output. The best example of this, and the one given by the surveys, is branch predictors, where you have this functional unit that isn't that has more information needed for it to come up with an output. Branch predictor is a good example of this because it has this history it needs to keep track of, and then based on its history, it creates an output. So in the case of branch predictors, and there's different types, given in the example of like a global history, where it takes track of like if a branch was taken or not taken, based on this history, it'll then determine whether it should take that branch or not until the actual result of the condition is created in the program. And then memory subsystem, this is the largest section in the background, where it covers each functional unit and what characteristics of those functional units create these side channels and covert channels. Caches has contention because the way caches are set up in modern processors, it has the ways and sets we covered in the last lecture. So then some different processors have to share those ways and sets, or they lead to the same spot, and so you have hits and misses. Then you have the table look-aside buffer, which is similar to caches, where you have this contention as well, because the virtualization from the actual physical memory to the virtual memory, it accesses the same location for these instructions. You have the prefetcher, where it tries to get extra data based on the data it's trying to currently get. So this can also lead to some information leakage, because some of that extra information isn't actually used, and it can stay within the cache. You have speculative execution. This kind of relates back to not functional, state-dependent output, where the best example is with a branch predictor, where it takes a certain path and it runs all that set of code. And then if it isn't used, it can get stuck within the process, which can be accessed by other processes. And then the other two, just to speed this up, is the memory controller, which has contention, and the interconnect system, which is more based on the instruction execution timing, based on how long it takes to reach certain memory, you know which type of instructions it's running. And then the final point is virtualization, and it doesn't go too heavy into it. It just mentions how this is important because you no longer have this physical proximity need, where your co-location for your channels can either be within the same operating system or virtual machine, or you can have a different virtual machine running on the same device. And that's the main point for virtualization. For coverage and classification of existing works, it kind of splits it into two main categories, which makes sense. The types of attacks you can have for these channels and the defenses for these channels. And within them, they have their own classifications. There's non-virtualized attacks and virtualized attacks. And what I found is that not all virtualized attacks work for non-virtualized situation, but some non-virtualized situations work for virtualized attack. That may be confusing, but that made sense when I was reading. So for cache, it's mainly different types of timing attacks. An example the survey gives is an AES S box, where it has certain for getting the encryption key, it has certain instructions it uses. And so when it goes into the cache, another attacker process can see what types of hits and misses it does to see what kind of encryption it's using. It's the sense I got. And you can do the same thing with instruction caches, and this is at an L2 cache level. And then the other important thing here in the types of work it covers is that the type of bandwidth you get from these different types of attacks is dependent on the level of cache the attack is hitting. So there's higher bandwidth at an L1 cache versus lower bandwidth at an L2 cache. Then you have data and control path units. Data path is related to like the example we saw last lecture with the ALU and the floating point logical unit, where there's contention or a process can stall the unit, so another process has to wait until it finishes to run its own execution if they're sharing these logical units. The control path is related again to branch predictors, where you know what kind of slow or fast path is taking. And then the system bus and interconnect, these types of attacks relate more towards more timing attacks, where dependent on what kind of memory instruction it's trying to access, or if a process doing some atomic operation like a write, then it locks the interconnect paths, and so you know what kind of the attacker can figure out what kind of instructions you're running. For virtualized attacks, they're pretty similar to the non-virtualized attacks, where for caches, instead of worrying between two processes in the same operating system, you could have a separate VM that's your attacker VM sharing a cache with another VM, and this way you can figure out what kind of instructions it's running and things like that. And then pretty similar to system bus and interconnect as the previous one as well. For the defenses, it separates it between a hardware level and a software level. And this is because the channels are created kind of as a hybrid of both. So you kind of want to find a way to protect the hardware so you're not creating these channels, or you worry about the software and try to find ways to detect these type of channels or attacks on these channels. And so for defenses, some of the works the survey covers is doing randomized caching. So if two different instructions don't map to the same cache way or set. For interconnect, it adds this limitation of how many instructions or what type of instruction a process can do on the interconnect, so you don't figure out which an attacker can't figure out which instructions the process is doing. And then some other minor ones it mentions are some hardware mechanisms, something like a hardware device to regulate resources between processes so that it's not all trying to use the same resource. And also adding some noise to like counters and other places such as the cache as well, so that it messes up the timing of attackers that are trying to measure the time of different instructions. And then at a software level, most of the defenses it tries to cover is flushing cache, flushing memory, flushing the actual history of the branch predictor, because this is most of the information leakage, but this comes at a performance cost where it makes the whole device slower. And then there's also deterministic instruction times, where in a virtualized setting, the hypervisor can kind of say, this instruction is going to take this long no matter what, or set it at the instruction that takes the slowest, and that way an attacker can't figure out the instructions since they're all timed the same. Yeah, sorry. Analysis, most of the analysis was done on the attacks, where it says that the history of attacks discovered or explored is based on the bandwidth size. So caches were attacked first, and then branch predictors last, because they have the least amount of bandwidth size for information leakage. It also analyzes that the main point of attacks that are exploited are based on contention. So caches or different processes sharing cache and so on. It has a theoretical high bandwidth channels are considered to be 100 bits per second. And this is important because through further analysis of different research papers, we've discovered we've way surpassed this limit. Some attacks reaching kilobits per second. And then this idea of having idealized attacks versus an actual real scenario attack, where the idealized attacks can be high bandwidth channel, while using that attack in a real scenario leads to a few bits versus its idealized version. and that new attacks don't necessarily mean they're higher bandwidth. Exploration of new attacks can just be in different functional units or areas that haven't been fully explored yet. For defenses, the analysis is between two different approaches. Do you design your defense at design time where you try to design new components or fix components that you know have certain issues to be better? And it gives these two main existing works as types of design time approaches, but it ultimately says that it's really hard to do because creating new hardware doesn't necessarily mean you fixed all channels. You could create new channels. And then runtime approaches, instead of trying to be preventative, you essentially try to detect these attacks as they're happening and then solve the attack before it gets worse. And then the open research problems proposed in quotation marks, because it didn't really propose research problems, but at the discussion on section 6, these are the 5 main points the survey makes of like, after reviewing all this work, these are like things that are left to do or what we've noticed that are still areas of research, such as the first one, it's relating to the timing of different instructions and how these lead to exploitation. The recent rise of this bandwidth threshold of 100 bits per second is being surpassed in recent times. This one is more open, where when you create new functional units, you can't assume they don't have these side or covert channels, as I mentioned. And then for functional units that don't have current attacks, doesn't mean they're free of attacks. They can still have some, or they're more related. They create paths for attacks. And 5 is that the defenses we have, main defenses is flushing information from the cache and branch predictor history and things like that. Then my main bibliography is the survey we read. Thank you.
Thank you, Steve. But good job is not done yet.
Yeah. I have, I'll go back because I think these are some good points to cover. But I think one of the first things I want to discuss, and I hope more people in the audience know some things about virtualization, because this is what caught most of my attention. Because at first I thought virtualization was an isolated environment, so it's difficult to attack. And so I found it very interesting where it said that different VMs can share caches, and I didn't know this was possible. I just wanted to hear some people's thoughts on that, on like, if you know why this is, or
So anyone like who want to comment on how virtualization works, like at very high level, you don't need to go into detail.
yes.
Yeah. Okay, so how many of you know how operating system shares the resources among processes? Those who have taken the OS course, I expect them to know how OS is doing that, right? So you can relate a virtualization to the same concept where OS is actually doing work that it is sharing the same hardware platform or same resources among multiple processes. So in virtualization, what we do is that we have virtual machines running different operating systems, but on the same underlying hardware. So resources are shared not among processes, but among multiple virtual machines. And the entity which is responsible for managing those resources is hypervisor. So what it does is that it allocates and manages the resources among virtual machines. But just like multiple processes running under the operating system, they share the components, like let's say caches. Same happens with the virtual machines, because necessarily the underlying hardware is same. So there is no there are no alternative resources. Same resources are shared. So as a result, what happens if you have read the paper carefully? What we have, the main one insight is if whenever there is sharing, there is a potential side channel. So still in virtualized environment, we are sharing the resources. So there are just other side channels which are exploited to launch cross virtual machines attack?
To jump in, I think from my knowledge of virtualization, right, you have these two different VMs and they don't necessarily run the same operating system.
Yeah,
So even if they share the resources, how could one determine what kind of instruction the other one is if you don't know its operating system per se? Like one is running Linux and the other is running Mac OS. How do you know? If you don't know the other one's Mac OS, how can the Linux attacker figure out what kind of?
Yeah, I am not exactly sure of the detail, but the basic philosophy is same because let's say if there is a virtual machine 1 and virtual machine 2, so they need resources for their execution, right? So which means they occupy, let's say, LLC, last level cache, or memory controller. So which means that if both are using the same LLC, one can affect the execution of the other. So focus of this paper is not going into details of like each and every attack, but focusing on the common aspects. What characteristics are there which actually help an attacker to discover a side channel, a microarchitectural side channel.
Right.
So if yes, they might be running even different instruction sets at the higher level of the virtual machine, but at the end, it's running natively. Something is getting translated and it's running natively on the architecture underneath. So if there is a thread or an adversary running, it can monitor what's going on. It can, as long as there is some shared environment, then there is potential for a side channel that could not necessarily steal stuff, but could just degrade performance. That's bad enough, right? So if you remember the Spectre and all of these sorts of things, at the end of the day, it's because there is a shared resource, whether it's the branch predictor or the caches. If there is a shared resource and you do not kind of protect it properly, then there is potential for attacks.
Right. Moving.
Yeah.
So when you said the memory and CPUs to a virtual machine is not actually specifically assigned to that virtual machine. So so if you said 8 megabytes of memory to a virtual machine, those 8 megabytes out of the total RAM from the memory on the computer are not exclusively to that virtual machine, but instead are shared among other.
I don't know, maybe Dr. Hamid can comment more on that, but even if, let's say, the memory is set aside, there are other components which still they are shared. Like memory chip, the capacity of, like, let's say, as you're saying, 8 megabyte, let's say, set aside for one virtual machine. But if you have one memory controller, then all the traffic is going through that memory controller. So it is again a shared component. So virtual machines can still expand.
And this is what you're talking about is basically virtual memory. Yeah. Memory looks to all processes infinite, right? So the assignment of 8 megabytes, just because you asked for 8 megabytes, you could ask for more or you could ask for less. But at the end of the day, the virtual pages will be allocated on the physical memory, physical pages, and there you could have somebody ask for much more memory than what it needs, and then it starts the other process, leading to degraded performance. That is a side channel. So the operating system or the hypervisor, depending on the setup, if it's virtualized, then the hypervisor, if it is even in a regular thing without virtualization, two processes, one process could, just because it requires lots of pages, just make the other one start. And then it is the job of the management, which is the runtime system, operating system, to maintain that. It becomes even worse when there is malicious intent, which is what this is talking about.
So what you're saying is that even if the virtual machine only has like 8 GB allocated to it, if it tries to access more, even though it technically can't, it can still affect the other ones by the physical memory, like trying to go towards it, or does it actually have some memory go into it?
So again, this would depend on the implementation, how the hypervisor and the virtual machine is implemented, right? Is it physically limiting it to exactly 8 GB total, or this is what it would allocate physically? But then the virtual memory is gonna work on the 8 GB only. And so there isn't, but again, the bottom line is there will be something shared. So there is potential for, if not stealing stuff, then performance degradation, and performance degradation is a bad thing when it's done by a malicious act.
So what Dr. is saying, to understand that you have to know how virtual and physical memory are mapped and what is virtual memory. But even if you keep those things aside, just consider like you have two processes and one of them is malicious. So what it does is that to hinder the execution time or to hinder the progress of the other process, and what it does is that intentionally it launches huge number of memory accesses. So if I am generating more memory requests, but you are a normal process, and the number of memory requests you are generating are the like how to say legal ones in the sense that you are not doing anything malicious. So I have more incoming requests, so I will be slowing down your execution. So that is like, yes, I'm not stealing any data, I'm not corrupting your data, but I am slowing down the execution of your process.
I think an example given by the survey is with the branch predictor, where you can train your process to figure out what the history is. And instead of saying, oh, I want to take your history, I'm going to say, oh, you usually take taken. I'm going to train your predictor to do non-taken to mess up and slow you down.
So it will also not steal your data, this example attack based on the branch predictor. But again, it will just make your execution worse in terms of like your application or your process will take longer time to complete because now maybe you are having a larger number of mispredictions as case to case where your predictor was not trained.
Right. And there's no more questions on that. I think another point I want to cover, and it's here, is the fifth point, where I don't know about everyone, but I was kind of surprised the lower amount of defenses compared to the types of attacks that exist. Where typically it's just, oh, try to limit the sharing or remove all of your existing data when you context switch out from your.
Can you say it again? I was taking.
Oh, that there's less types of defenses compared to the amount of attacks there are. Like the two main ones that I've understood was either you try to limit the sharing, or you basically flush or remove the existence of work done by your process until you get back to it, which slows down performance. And these are like the only types of defenses that exist. I was trying to wrap my brain around why couldn't there be more, or why isn't there more work about different types of defenses?
So I guess those are like, those are two basic approaches. Like if I leave behind a footprint, let's say I'm a victim process, and I leave behind a footprint, that footprint can be exploited by the attacker. But if there is a mechanism or a defense technique which can actually get rid of the footprint, then there is nothing for the attacker to exploit, right? So the thing which you said, like flushing the caches or flushing the TLBs, so it is an approach where you are getting rid of the footprint left behind by the victim. Yeah, and talking of the flushing, can anyone comment on like what could be the problem of this approach? What is the downside?
I mean, like, we need to reload,
it will create cost, it requires to hold other processes. By this time, we can,
Yeah, so like, I mean, it's like normally what happens that when you develop a security mechanism, so not all the time, but normally what happens is that you are sacrificing the sacrificing the performance as a cost. So for example, if you flush the here, these are caches, or even like if you do partitioning of the caches among multiple processes. So now what is happening is that for one particular process, the effective size of the cache available is reduced as compared to the case where you are not partitioning. Yes, partitioning give you a security, it will improve the security level, but it will also affect the performance. So there is a trade-off. And same goes for randomization. If you have randomized cache. You know what I mean?
So the best solution for this problem will be on the redesign of the hardware or better programming habits, or in a middle point between those two, where those two are balanced.
You need to focus on both when you are designing your new architecture or any new architectural component. So you need to take into consideration that, okay, what kind of side channels my design can introduce, new side channels my design can introduce. And when you are like, as said in the paper, like side channel is like a kind of hybrid thing where both software and hardware are involved. So when you are writing your program or your code, you need to be aware of how my program can end up in leaking the information, right? And how I can avoid it. So like, but again, it is not like a never-ending war. So you will develop some solution, but then maybe you generate or introduce new side channels which you are not aware of, and an attacker can discover them and then exploit them for a new attack. Yes,
So the channels can't be completely eradicated, right?
if you have no variation, like let's say if you have, for example, no variation in execution path. So everything is like uniform, then there is no information you can extract. But then if you do that, then it means like you are sacrificing the performance. For example, if I say that, okay, all my instructions in my program, they will take the same amount of time to execute. Now, there is no timing difference in the execution of the instructions. So I'm not giving any kind of like timing information to an attacker. Yes, so, okay, I can protect my program, or I can protect my hardware, but then if I restrict every instruction to take same amount of time, I'm wasting my resources. So basically, I'm wasting CPU time, and it will take longer for my program to complete.
Also, I think there an interesting insight related to that, also from the survey, is that I think most computer scientists will always try to find an optimal way to do things, and this leads to more optimized performance will always lead to more channels. So I don't think it'll be completely erratic, or there's no way to get rid of them, because more components are designed to make the processor faster, and then you create channels because of that. Is an insight from the survey.
So, I mean, normally with security, there is a cost to be paid. There is no such thing as a free lunch. So if you want performance, pure performance, then you have to sacrifice some other thing. If you do not share resources, yes, one application will do well, but others will not do. And if you share thing, you might have an application that needs more. Imagine you are sharing a fridge with a roommate. If you hard share it, like half and half, you have two drawers and two drawers. If you have more stuff, you need a third drawer. The other guy is not using it, so it's a waste of resources not to use that third thing. So there is always a cost, and what you optimize for is you try to have the best security you could without a whole lot of sacrifice of performance, and that's almost impossible. There has to be a cost to be paid. It's a design point. What can you do? And again, Spectre, if you have looked at it, was in order to get rid of it, they had to do something that made performance suck. So See something about different process for the executed. And specifically from that, do you kind of give it another process for the schedule or something before the development process tries to execute something certain? Is that what kind of base effects work?
So the basic idea of the timing based attack is like what you do is that your attack is based on some measurement of the time which is taken for the operation executed by the victim. So like as in last lecture, I mentioned, like what you can do is like, let's say you have two processes, A and B, and they have their program running. And we know that how data is mapped into the caches. So if we know that, okay, these particular addresses will always be mapped into these particular sets of the cache. So what the attacker can do is, like, let's say it can first fill the cache, those particular sets. It can fill with its own data. And then it can, let's say it can go to sleep, it can itself sleep. And now the other victim process, when it is scheduled on the same core and it accesses the cache, and it kicks out, if it is also using the same sets, like for mapping its own data, it will kick out that data of those cache lines from those sets. And then the attacker will come back and try to access its own data. It will see, okay, I left behind my data here, but now it is not available. Before I went to the sleep mode, and now it is not available. How it can find it is not available because it was expecting that it can access the data in lower amount of time. But now it is not available. There was a miss, and data need to be brought back from the lower level of the memory hierarchy. So this timing difference now gives you the information to the attacker that, okay, the same cache line is used also by another process. Now, how you can use this information, it is a different question. But here we are like focusing, okay, how the shared component can be exploited by an attacker. So this is like, again, timing difference is the tool which you are using to construct that.
Another point for the defense that I had written down is that when I mentioned that there's a design time approach and a runtime approach, that one of the difficulties with design time approach, to get specific, is that we have no metric, or we have no way of detailing how do we figure out what type of channels could exist. We have no, what's the wording I'm looking, like set of rules to say, oh, we can know a channel exists if this component has this attribute, and this attribute. Besides, oh, it might share them. Like this might be a shared component. And so that's one of the difficulties with creating a defense at design time. And I kind of wanted to talk about that a little bit, or open it up, because I found this interesting of like, maybe we not really come up with a solution, but like, if we just talk about it, like what would be the metrics at design time, if that makes sense? Like just looking at a component itself, what would make it vulnerable or create channels from it? I don't know, that wording made sense.
Yeah, I think maybe anyone before I give my thoughts. Anyone who want to talk about how we can figure out, can we design a matrix to find out, okay, I have this component A, and can I use a systematic approach to find out whether it can make a side channel or not? I mean, definitely,
Yeah.
it will not be like, foolproof.
Yeah.
First attempt.
It will be really hard to detect those kind of channels.
But you can reason about them a little bit.
That was the word reason.
Yeah, we need some starting point for the thought process to go.
I think for me, naively, I kind of briefly passed by it, is the fact that we know most of these is that they're shared, right? That these components get shared between processes. And I think that's one thing we can reason about, or like dive into, like, okay, do I know this component will be shared? then I can determine. Oh, good.
So if you are designing a component and if let's say you are running two applications or let's say two processes, and the sharing among those processes for that particular component is above a threshold. Now, how you measure the threshold or how you measure the level of sharing is a different question. But let's say if the sharing is like significant, then it means that it can become a potential side channel, right? And another thing they have mentioned in the paper is like, there is a direct relationship, I think in discussions. There's a direct relationship between the amount of performance optimization or improvement offered by a component and how frequently or how easily it can be exploited for a side channel. And that very typical example is caches. So caches, because they give the performance improvement and major performance improvement, and they are also, that's why, very attractive point for developing side channels. So there are many attacks which actually utilize caches for side channel. So this is like you can think about when you are designing a component, okay, how frequently it will be shared, how much performance improvement it will give, because more performance improvement mean, remember, there are two things they said in the paper. One, first, if there are low and fast execution paths, and second, the contention or sharing. So if you are giving, your component is giving more performance improvement, it means it is creating a significant difference. Like it is giving you the fast path, more optimization, more faster. And lower optimization, less difference. Right.
Question about that. So since it is more like a give and take, and more in this article, I kind of like started when I started reading it a lot more, they kind of went away from the hardware aspect of it. They went towards more of the software aspect, and I was wondering like why would they take more from the hardware and give more to the software to better enhance it, even though knowing that they're going to get the diminished hardware like security of it.
You're talking about defenses? Yeah, so say, do you want to respond?
Yeah, you correct me, because I'm going to rephrase to see if I understood. So you're asking, if we know we're designing these hardware for, say, performance, and we have these security risks, why are we having software compensate for that? Other way around. You have slower hardware for better security, but you want software to make it faster?
Getting this backwards.
What do you mean by better performance in software?
So I think I might be getting myself backwards here in a sense.
So describe it with an example that would make it easier for you.
I don't know how to put it. So,
Fictitious.
so saying like here, saying the longer the application can keep, so in the article it says the longer the application can keep the resources, the better the leak protection, but also the more negative of on performance of other applications.
So
Translate that, can you?
Yeah.
What
Let me
he
explain.
meant?
yeah,
Explain. The statement you read, it is basically in context of flushing, so as a defense. So once you flush, so let's say I am running my application, and after I am done with my execution, all my cache lines and T of these, they are flushed. Now your application need to run, right? So now then you need to repopulate the caches with your data and T of these with your translations, right? So if I frequently, the time allocated to your application is smaller, let's say you get only 1 second, and after that you are kicked out. Again, the flushing will happen, and again, I'll need to repopulate, right? And again, after 1 second, you come back. So there will like, again and again, flushing happening, and as a result, what will happen? The performance will decrease. However, if it is the case, like you are given not 1 second, that I'm making an extreme case, you are given 1 hour, okay? And then So initially there was flushing, and then after that, for 1 hour, you are not disturbed, are not interrupted. So yes, there was the impact of the flushing, but in this case, where you have longer time, now you can benefit more from the locality in the caches and from the TLPs. Before,
Basically,
yeah, you will flush.
because the time grows, your overhead becomes much smaller given the time you are given. That's why it makes a difference. If you are not context switched for a long period of time, then the overhead of all the flushing becomes negligible compared to the large time allocation you got. And then also it becomes less of a security threat, right? Because you are not giving away anything, you are holding to your portion or to the hardware you have, so nobody can read it or nobody can read anything out.
I think related to that, like, it also depends on the case, like in my mind immediately goes to like real-time operating systems where you have a process that stays on longer just naturally because that's how real-time operating systems usually work. Where you want one process hogging it until another process like emergency needs to take over. So then that's like a good case of where you can flush the cache. It's like a real example I can think of.
Another thing with real-time operating systems is it's deterministic. Because you cannot allow for something like a cache to be very undeterministic, and then you have no guarantees on response. So that determinism is something that's good and bad, like, right? It's good because it is deterministic, you know exactly how long it will take to get something from memory, but also makes you predictable.
Right.
I think this is the question.
So the fact that the leakage rate from 100 bits per second has increased, is that related to how computational power has increased over the years?
It can be, but I think more it is related to how the capability of the attackers or capability of the attacks has increased over the time. So attacks over the time have become more sophisticated. So for example, if you, I assume you have that. So the first attack which they reported, it was like its bandwidth or its leakage rate was like only 0.001 bit per second. But now they have attacks which are like kilobits or even megabits per second bandwidth. So that is both related to hardware improvement because more optimization you perform, more information you leak, and also the techniques which are deployed by those attacks to exfiltrate the information. So it is the combination of both.
So attacks are appearing faster, or these kind of vulnerabilities are appearing faster than we can fix them?
Can fix them and
Well,
so say it again, I don't understand.
Normally, there is no fix until there is a threat vector or an attack vector already existing, right? So sometimes you don't know that there is a problem until you see that there is an attack.
Yeah.
And historically, like SMT was mentioned in the paper, I looked quickly. SMT, when it was designed, it was purely a performance thing. If you read Dean Townsend's paper, it's like 1998 or something, purely performance thing. All what they looked at is how to squeeze the hell out of performance from your out-of-order processors by running multiple things so that you have better throughput. No security thinking whatsoever. Security normally comes a little bit after. Now, security is becoming a first-class citizen in most of what you look at things. But before, it wasn't even thought of. Nobody, when that paper was written and submitted, nobody among all the reviewers thought of any security, anything at all. So the security and what happens evolves over time.
So another example, like same like that, I just wanted to go here. We were working like on persistent memory. So our first question was like, okay, how can we develop an abstraction which can efficiently access the persistent memory? And when we say efficiently, it's mean we were focusing, you want to access the persistent data, so how we can reduce the latency and maintain the correctness. So we like that was like first paper, and then the second paper, and then after that, security was an afterthought. Okay, now we have this abstraction, but how an attacker can exploit this abstraction to launch the attacks. So first, our first performance, and then we are playing the role of the attacker. Okay, now we have a paper of attack. Okay, how we can now defend against this attack? So security normally comes up like, as an afterthought or as a second step, or maybe once someone has launched a successful attack, then you think about, okay, how I can transfer. But it should not be the case, especially when it is.
It complicates the design, right? If you are gonna take it from the beginning, it's going to complicate the design. If you cannot think of an attack, then why should you consider it to begin with?
Yeah.
So one question that I kind of have is, there's only like so much you can do with software to like have changes in hardware, be more secure. So I'm wondering where firmware like lies in that security thing. So if you can't like make a hardware change with software, what like are there rules you can set in the firmware that are going to prohibit access like in a virtualized environment for like hardware, like two virtual machines that are on the same machine? Is this something you can do in the firmware that'll make it much more difficult for like resources to be leaked, like in the memory or something like that? I'm not sure if that's a clear question or not.
Yeah.
You know, well,
So for example, in the context of memory, like when you are writing, doesn't matter whether firmware or the program. So there are some programming practices that you need to follow. So specifically when you are dealing with memory. Like for example, if you are using, you are writing a program in C and you are using pointers. So you need to be very careful, like when you are allocating the memory, then you need to be sure that pointers are checked for sanity, like there are no dangling pointers, or you are always referring a memory which is already allocated, or like for example, if you are using any kind of input buffers, so you maintain a check on the bound of those buffers. So otherwise, because it can end up in situation where it can corrupt your memory, not only corrupt your memory, it can also create situations where the memory accesses or malicious memory accesses can be exploited to hijack the program or process. But then there are protection mechanisms against them, like where you don't allow your memory to be overwritten or overflow. So it doesn't matter whether it is firmware, but then the other regular user code or user application. But the code you are writing, you need to keep all these things in your mind. There are also tools which can actually check your software or your program that whether it has anything, this kind of vulnerabilities or not.
So I guess kind of what I was meaning was,
so
like it's
I
expensive.
think I got some, so here what I have to say and then I respond. So again, I'll go back to the S&P example with the hyper-threading. There is a setting in the firmware where you can disable hyper-threading if that is something that you are willing to give to have a more seemingly secure thing because there is some leak or something. So there is some settings in the firmware that will disable or enable things sometimes. Right? Maybe thermal management. You have a thermal problem and thermal management is hurting, so you can disable that and so on and so. Yes, so there could be some things that you could do in the firmware. Basically, the BIOS, if it's a machine, you disabled or enabled some functionality that can have an impact on performance and or security.
Okay. So maybe we can have one last question or comment suggestion before we go for form submission. Thanks for the.
So I think that, the defense, it's talking about the randomized cache being, like, it's really good for the external timing, but the internal timing may, like, still be an issue. Why would the internal timing cause an issue, but not the external timing cause, not cause an issue?
Yeah,
Um,
I specifically noted this question and I don't know the answer, to be honest, so.
Uh,
So, but let's have a like deeper look on how this randomization works. So in randomization, you are saying like, what you basically do is that without randomization, the normal cache, what it do is that if you know the address and you know the mapping scheme, you can tell that, okay, this address will be mapped into this particular set of the cache. So if I can predict even the address, if I can predict that, okay, this address will be is going to this particular site, then I can, how to say, use this prediction for malicious intent. So then randomization is like, okay, there is no, at the runtime, we will decide whether this address will be, given address will be mapped into the set 0 or set 1 or way 0 or way 1, right? So if it is randomized at the runtime, then there is no deterministic behavior or prediction possible, right? Now, coming back to the question, what was the question? Whether it gets rid of internal timing or what?
But like, why is the internal timing an issue, but external timing isn't?
Okay, so external timing is where you are measuring the timing of the victim, while the internal timing is where you are measuring your own timing, right? And you are an attacker. I'm not sure, maybe because the reason could be like, if I'm an attacker and at the runtime, I can find out that how long it takes, I can measure how long it takes from a particular address to be mapped into a particular into a particular set. Then maybe I can use that information, but I noted this question and I'm not,
my thought process for it was, I guess depending if you know what the algorithm for the randomization is, instead of measuring how long the victim takes to do cache hit or miss, you figure out, okay, my thing maps to this way or set, and then dependent if another process does it, like, can I figure out the algorithm of the randomization based on like, if I'm the second process to initialize or the first one or something like that.
So you're saying that it is more about figuring out or decoding the algorithm as an attacker instead of
Yeah,
focusing on the timing of the victim.
figuring out the randomization, so then you can better, well, I mean, this is just speculating, manipulate that information to figure out, oh, this process is trying to,
Maybe we can have a better understanding of this question if we know how the more details of how randomization is implemented and how it works. Whether the address is known at the runtime, whether the algorithm is a common knowledge for both attacker and the victim, or is it like not an open source? So then, but at this point, I also don't have an answer. Okay,
I have a question about building on that with kind of the randomization, because they talk about using security and obfuscation a lot in the caches.
yeah.
But how, if you have two open books and they have, like, say you're hashing this or something in the cache, how is obfuscation helping in securing anything if I can just find the key to unlock the cache, if that makes sense?
If I can find one.
If you're, well, I guess, how are we obscuring stuff in these caches from other processes, from an attacker? If the attacker can already see the memory, but we're gonna have to have some kind of key to be able to obfuscate our memory. So would the attacker just be able to find it? Is it just to make it more difficult?
Yeah, the issue is that with the randomization, now attacker will not know that. If let's go back to the same example. So, which I quoted last time. So if you are given an address, in advance, you know where it will go. And now you are an attacker, so you can know that, use this information. But if I totally change my mapping algorithm and I randomize it, and at the runtime it is found where this address is going to be mapped, now you don't have that prior knowledge available. So if you don't have that prior knowledge available, then you cannot know that, okay, if, again, let make it more concrete. Let's say you are an attacker and your address one was mapped at way one in the cache, right? And you were saying, okay, now I will fill this cache line, and then I will come back and check whether I find my data or not. And I am the victim. I also have address one in my address space, right? But due to the randomization, my address one is not mapped into the way one, maybe it's mapped into way, let's say, 10. Okay, so when you come back, you will still again find your data there. So this is how it like makes difficult for the attacker to infer any kind of information.
So it's stored, we're not obscuring the data itself, we're changing where it's being stored.
Nothing,
Okay,
nothing, not the data itself.
understand.
I think we need to start because then now you need to submit the class participation form.
Wasn't there another way of obfuscation where you present random noises or random delays to?
Yeah, so an example is like in the paper, they mentioned that it is more easier for attackers to exploit L1 cache as compared to last level cache. Because L1 cache is normally private to a core. So if it is private to a core, so, and two processes over the time are interleaved on the same core, there is less noise as compared to the case where you have LLC and it is shared among all the cores. So it is shared among all the processes, so it is polluted over the time. So if victim is leaving the footprint in the LLC, by the time the attacker comes and tries to manipulate that footprint, it is already polluted. So, okay, now go ahead and do your submissions. What time is it, by the way? 4:08. Okay. Nadia, can you extend the submission time by 5 more minutes? I have a quick question for that. After the discussion, you for next week. Okay, I don't want to put pressure on you. You can you can tell me later in my office.
Actually, was having trouble with registering, which I wanted to discuss with you.
Okay, we can do something.